So now we're going to apply the Reynolds transport theorem to conservation of mass. Okay, and recall that conservation of mass is that the time rate change of the system that is following a particle or something around, which is how you guys have used it until then, with the exception of thermo, is that the time rate change of mass in your system is zero, or mass is conserved. And recall that the mass in the system is just the volume integral of rho dV, which is our generic formula with eta equal to 1. So we apply the Reynolds transport theorem with eta equal to 1, and we get that the time rate change of mass in our system is equivalent to the time derivative of mass inside the control volume plus the net amount of mass leaving through the control surface. Okay, and that's equal to 0. And this term here, as I just sort of stated, this term represents the accumulation of mass in our control volume. And the second term here it represents the net mass flow rate leaving out through the control surface. And so conservation of mass dictates that basically this derivative, which is equivalent to these two terms here, is equal to 0. So the conservation law tells us to set these two terms equal to 0. And this here is called the integral form of the conservation of mass, or continuity. Okay, and so draw a big box. Draw a big box around the integral form here. This here is the integral form of a continuity. And you guys were actually using this all along in thermal without really even knowing it. And now there are some common assumptions. And again, this looks big and scary, but we will get used to doing those surface integrals and the volume integrals. Okay, and some common assumptions, I already listed quite a few of these. There's steady flow. That just means that the partial derivative of n in the system, or the control volume, is equal to 0. That basically means we can drop out that term. And I expect you to show that every time. You can do incompressible flow. That just basically means, most of the time that will mean that the density is equal to a constant, but that's not always the case. So in general, you can think of it as just that the volume of the fluid is preserved as the system moves. So that is, if the system is sort of wiggling about in space like this, that the amount of volume in the system does not change. Okay, that's basically what it means to be incompressible. Okay, but if the control volume is not deforming or anything like that, that just means that the volume of fluid in the control volume is constant. Okay, and so you can sort of derive an incompressible version of conservation of mass, assuming that rho is equal to constant. Even though that's not, strictly speaking, an incompressible flow isn't quite that. Is that it's a bit less restrictive than that, actually. Okay, so we assume density is constant, which means we can basically, for the purposes of derivation, we can basically yank that out of the integral and the time derivative. And in your guys' homework, I expect you to show this step. I want you to start from this generic form, and I want you to argue that density is constant, so I can pull it out of these integrals. I want you to show that every single time. Okay, then I can work with this a bit more. This implies that the integral over of density times the time derivative of the integral of dv, and this here is just the volume, plus the integral of rho times the surface integral of v dot n hat dA is equal to 0, because this is still just conservation of mass. There isn't anything special about it, but density is constant, and we have the same density here as we do here, and the right hand side is equal to 0, because that's what conservation of mass stated that. So that means we can cancel out these two densities here, and basically this entire integral here is volume, and if the control volume is not deforming, then that means this volume is constant. So CV is not deforming. Okay, which means that the volume of fluid in the control volume is not changing. Okay, then this implies that for incompressible flow, we are left with just this term here. If the control volume is not deforming, if it's deforming, then you do have to account for the change of the volume of the control volume. Okay, but in general, but in most cases, you will not be deforming the control volume, and our incompressible conservation of mass just turns into this expression here. Yeah, I might as well box it. And again, you can only strictly use this one if the control volume is non-deforming. If it's deforming, then you have to include, then basically you cannot, is that dV dt will not be equal to 0. Okay? And we will have an example with that, and I will show you what to do with a deforming control volume. But for now, to get your feet wet, we will be doing non-deforming control volumes and stationary control volumes, just to so you guys can get used to these. Okay, and the other assumption that I hinted at earlier is called uniform flow. And uniform flow means that basically V, rho, P, T, etc. at an inlet and outlet is basically spatially uniform. Okay, and so we could consider a goofy pipe junction here, where you have some flow going in here, flow going out here, and flow going out here. And if we are to apply, if we are to find the surface integral of rho v dot n hat dA over this, we would basically need to walk over the entirety of the surface and basically accumulate all of these pieces here. Well, we have an area 1 here where flow is going in, an area 2 here where flow is going out, and an area 3 here where flow is also going out, and some so-called sides. Okay, so we need to, so when you do these integrals, we need to walk around the entirety of the control surface, and you need to make sure in your homework and your quizzes that you completely enclose the control surface. Okay, and so with this, we have completely enclosed the entirety of the control surface. And if we assume that the walls are impermeable, which means that V dot n hat dA, or V dot n hat, is equal to 0. Or in other words, that no mass is crossing through these impermeable walls. That's another very common assumption that we'll be making again and again and again. Then if the flow is uniform, that basically means these quantities over these inlets and outlets are basically spatially uniform, and we can yank them out of the integrals. Okay, so we can basically pull these outside, we can pull these outside, and we can pull these outside. And again, in general, you may have, say, surface 1 is uniform, but maybe surface 3 is non-uniform. So, so you can only apply this to a certain subset of surfaces. And in your homework, I expect you to start from here. And I want you to show that you are arguing that the flow is uniform. Therefore, you can basically pull out this. You can pull out the inside of the area integral outside of it. Okay, I want you to start from there and make your assumptions and then apply them basically very rigorously. Okay, but if we simplify this and basically basically apply the uniform flow assumption on all three of these surfaces here, we have rho 1 v1 dot n hat 1 times the integral of A1 dA1. This is just the area. And we have the same thing for the second area here, and the same thing for this third area here. Okay, and in your classes in heat transfer, especially, we will call this an m dot double prime, and this m dot double prime, this means rate per unit time. And this double prime means per unit area. So this is called a mass flux. And I'm not going to talk about fluxes too much in this class. In your guys' heat transfer class, which you guys will be taking sooner or later, you guys will be dealing with fluxes quite a bit. Okay? So, and so, in other words, this rho v dot n hat is just a mass flux. Okay, and the integral of an area, the integral of basically dA, and basically nothing multiplying dA, is just simply the area. So we have just mass flux times an area. And so this entire surface integral here reduces to a sum of the mass fluxes times all of the areas. And this here is just m dot going in, so that's m dot 1. This is m dot 2, which is leaving. And I just leave this as basically m dot 2 because basically the velocity in the n hat will take care of whether there is a plus or a minus sign in front of it. Okay, and this is m dot 3, or this becomes m dot 1 plus m dot 2 plus m dot 3, and this equals the sum of m dot over all the surfaces, which is essentially what you guys used for steady flow in your thermal class. But in this class, I never, ever, ever want you to start here. I want you to start here. Okay, and in general, I want you to start from the full integral form of the conservation laws. And after we introduce deforming control volumes, I want you to start from that version, because you can. Okay, so now we got all these. We got this crazy integral relation. How do we actually use it? So, as an example, we're going to do an example now. So we're going to say incompressible flow is developing it in a pipe of radius r. And at this station here, we have a perfectly flat profile in the pipe. And the velocity here is uniform. And it is going in the x direction. So that is u I hat. Okay, and we're going to define r as going out from the center line of the pipe, and cap r as the radius of the pipe. And then at some downstream distance of the pipe, we have a velocity profile at station 2. And that velocity profile is given by u max times the quantity 1 minus r over cap r squared, like this. Okay, and of course that's in the I hat direction. Okay, and I'm going to define x, and then I'll just call this y. Okay, well, which you should use a cylindrical coordinate system, but I'll just call that y for the purposes of this class. Okay, and so what we are asked is, how is the magnitude of this velocity profile here? How is that related to the peak velocity downstream? Okay, so how are these two related? So what we are asked to find, so that would be the givens. What we are asked to find is the relationship between cap u and u max. And so our assumptions are, we need to assume steady flow. Okay, so we're going to flow we're going to assume steady flow, which means that the time derivative of any quantity is equal to 0. We will also assume incompressible flow with constant density. And also, I'll make a third one, and that is impermeable walls. Okay. So now, how do we go about doing this? Well, you start by applying your basic conservation principles. So here, Newton's second law isn't going to help you. We didn't do anything with it anyways. Bernoulli isn't going to help us. Fluid statics is not going to help us because because there is moving fluid, so we can't even apply fluid statics. So the only principle that we have at our disposal to solve this problem is conservation of mass. And so to apply conservation of mass, we start from the generic form of conservation of mass, and this will become slightly more complicated as I introduce a deforming control volume and a moving control volume. But the solution is to apply the integral form or the Eulerian form of the continuity equation, or conservation of mass. And conservation of mass reads that the time derivative of mass inside of the control volume plus the net mass of material leaving through the control surface is equal to 0. Well, we assume steady flow, so that means we can cross out this term here. That's steady. And in your guys' homework, I want you to start from this expression here and explicitly cross these terms out. Basically, just like I'm doing right now. Okay. So what we are left with then is just the surface integral, and if we are assuming that the density is constant, that means that we can basically pull out this density, and basically that means we can basically yank it out. It would multiply the outside, and the outside is equal to 0, so we can just basically cross that out. So that does not contribute. So this implies that the surface integral of v dot n hat dA is equal to 0, or the net volumetric flow rate if we go around the entire control surface is equal to 0. Okay. Again, I expect you to start from here every single time. Sorry, I'm left-handed, and iPads do not like left-handed people. Okay, and so with these types of problems, I expect to see a control volume every single time. Okay? So we draw a control volume. Okay, and so our control volume is quite simple. It's just a rectangle. It's actually a cylinder, but I'm not going to draw that, so I'll just draw a rectangle. And we are understanding that this is just a cylinder. And again, the control surface must be a dashed line. Okay. And then we draw the velocity profiles at the inlet here. So at this station here, we had a perfectly uniform flow. And I will call this station 1. And at station 2, we had a velocity profile leaving it. Okay. And so we could say that V1 equals U I hat. And we could say that V2 equals U max times 1 minus R over cap R squared I hat. And in general, you don't have to put these long expressions here by the velocity profiles. We could just call this V2, and I'd be fine with that for homework. Okay, And then this here is station 2. Okay, and now we got station 3, which is the sides, and these are the walls. Okay, and so we now have station 1 here, station 2 here, and the walls. So we have completely enclosed the control volume. And now we need to complete this integral here, meaning I'm going to need n hats. And so now we're going to apply the rule that I discussed last time. And so we're going to walk around the control volume. And n hat always points out. So if we are here, n hat 2 points in the I hat direction. And if I continue walking around and I come back around to station 1, well, n hat here points to the outside, and here, the outside, n hat 1 equals minus I hat. Okay? Okay, so now we know n hat, v on all the surfaces, and we've completely enclosed it with all the different stations. So now we can start working with the integral. So first we'll take we will take the integral of v dot n hat over the entire surface, and then break it into the sum of the surface integral over all of these little pieces here. So this here is the surface integral over just this piece here. This here is the surface integral over just that piece here. And this here should be 3, not a 2. This is the surface integral over the walls. Well, we can get rid of this term here, because that's the walls and that's our impermeable. Which means v dot n hat is equal to 0. Okay, and if v dot n hat along the walls is equal to 0, that means that entire integral goes to 0. Great, so we have taken this sort of nasty surface integral, and we've already gotten rid of most of it, and we just need to consider this piece here and that piece here. And so now what I like to do is basically this portion here is just a lot of bookkeeping. Okay? And so now we basically need to find each of these integrals. So we find each integral, and I'll first work with area 1, and that is an inlet. And so here I like to because we want to find v dot n hat, is I explicitly write down v1, its vector, and I explicitly write down n hat 1, and I take v dot n hat 1. Okay, so v1 is u I hat as defined in the problem statement. N hat 1 is minus I hat, because again, n hat points outside and it's normal to the surface, and so outside points to the left, which is in the minus x direction. Okay, so we now know n hat 1 and v1. We can take their dot product. I'm not gonna explicitly do that, but this implies that v1 dot n hat 1 is just equal to basically minus u, because this turns into v1 dot n hat 1 equals u I hat dotted with minus I hat equals minus u. Okay, so now we're going to take this and substitute it into this integral here. So we got the area, we got the integral of v dot n hat over area 1. Well, that is equal to the integral of minus u dA1. Well, this u is constant, it's not a function of basically where we are on the surface. So that means we can yank it out because it's spatially uniform. So this equals to the integral of minus u times the integral of dA, and that's just the area. So that's just equal to minus u times a1, and a1 is just pi r squared, right? Because it's just a pipe of radius r. So then this implies that our first integral here is just minus u times pi r squared. Okay, and so we have completed these pieces here. So we have walked around almost the entire surface. We just have surface 2 to deal with, and then we will have completely walked around the surface of the control volume, and we need to just do that piece, that integral there. And most of the time, your surface integrals and your pieces will just turn into basically a velocity times an area most of the time. Okay, but I still want you to go through this procedure every single time, because again, in practice, you will not have such nice flows to work with. You will have complex flows, and you'll have to actually integrate over the surface. And I'll show you how to do that now. So now area 2, that is an outlet, and I guess how you could define an inlet is a section where flow is moving through a surface, and the velocity in n hat and v dot n hat is negative. An outlet is where v dot n hat is positive and there's flow moving through a surface. Okay? So now we work with area 2. Well, we know that v2 is equal to our basically function over it. And notice it's nice is that it's somewhat nice in that it's a function only of the radius. There's no azimuthal or theta dependence. So that's nice. We don't need to, it's not super nasty. And we know that n hat 2 points out from the surface. And so that means it's pointing to the right. So n hat 2 is I hat 2. Then this implies that basically v dot, basically the velocity vector at station 2 dotted with n hat is equal to u max times this function of r. Okay. Now we take this result and substitute it into this integral here. So we do that. The integral over area 2 of v dot n hat 2 dA2, well, that's equal to the integral over a2 of u max, which is just a constant, times this function of r here. Well, unfortunately, this is a function of r, so we need to actually do this integral here. And so to do this integral, we first need to define what a2 is, because again, this velocity, it is not spatially uniform. It is non-uniform. We cannot pull that outside of the control volume. But notice this is only a function of r. And if we look at a sort of a 3D-ish view of our exit surface, we notice that in this ring here, I've got to choose a different color, that in this ring here, this function of velocity at this ring is constant, okay, because it is only a function of r. So we can define dA to be the area of a differential ring. Okay, and so that means that dA2 is equal to 2 pi r dr, or you could do the or you could break it into little angle chunks too. Either way is fine. Okay, so now we know dA2, and we substitute that in. So this means that the volume integral of v2 dot n hat 2 dA2 is equal to the integral over the area, which is of basically this function here, which is just the integral of 0 to r, 2 pi r dr. And we pull out what's constant, and that's just the 2 pi and the u max. So we can pull that out. And we need to integrate this function here. And that's pretty straightforward calculus. I'm not going to show that. It's just a polynomial. After you basically after you distribute this r, I'm not going to show that in detail. I'll just sort of skip ahead. And this integral turns into this function here, and I simplify it, and we get that the area integral of v dot n hat dA2 is equal to pi r squared over 2 times u max. Okay, so we know both of the integrals, or both of the non-zero contributions to the surface integral. So finally, we have that 0 is equal to the integral of v dot n hat dA over the entire control surface. And the only contributors to that for this problem was the integral, or really the volumetric flow rate through the inlet and the volumetric flow rate through the outlet. We formed both of these integrals, so we can just substitute in the results. And we wind up, we'll erase that line. And so I substitute that in. This here is the result for A2. This here is the result for A1, which is right there. We substitute them in. These are equal to 0, so we have a pi r squared here that we can cancel out with the pi r squared here and solve for u max. And our final result is that basically u max is just twice u. Okay, and this here is not a contrived velocity profile. It is one that we will be dealing with in pipe flow in chapter 8 quite a bit. Okay, and so basically this means that in this velocity profile here, this peak velocity here at the center line of the pipe is exactly double that of the mean velocity in the pipe. And that's a pretty common result, and we'll be using that one quite a bit later on in class. Okay? So, and I'm going to do one more problem to show you how to use it. And so here, this is an example of a case where we need to apply the incompressible flow assumption in addition to using the normal conservation of mass. Okay, so here is an example. We have a mixing tea, where in one leg of the mixing tea we have water coming in, and on the other leg of the tea we have alcohol coming in at a specific gravity of 0.6 and a volumetric flow rate of 0.3 cubic meters per second, and the volumetric flow rate of water coming into the inlet here is 0.1 cubic meters per second. And this chamber here is large enough to allow the water and alcohol to mix, and we basically want to find what is the density of the liquid basically leaving what is the density of the liquid leaving the surface. So here's a case where it's a liquid, so we have incompressible flow, but we have a different density here coming in this side than we do on this side. And then they mix, the streams cross, if you will, and they mix, and they basically leave with a uniform density leaving the other side. And we're asked, what is that uniform density? Okay, and so that's what we are asked to find, and here we need to write the assumptions. We're going to assume steady flow. We're going to assume uniform flow at the inlets and outlets. We aren't given anything else to deal with, and so we do need to do that. And we're going to assume incompressible flow. And the fourth one, we'll assume impermeable walls. Okay, so the solution is we need to apply conservation of mass, and to do that, we need to draw a control volume. So here I just drew a pretty bad control volume following that T. We have some velocity 1 going in where there's pure water, some n hat 1 pointing out, some velocity at station 2, which is the alcohol inlet, and some velocity or n hat 2 pointing out. And we have the outlet where the alcohol and the water are mixed, and we don't know the volumetric flow rate there. We don't know the specific gravity, but we know that n hat 3 is just some n hat 3. Okay, so first things first, for problems like this, apply conservation of mass and see what that tells you. In this case, it's not going to be enough. We need to apply another assumption. Okay, because incompressible flow can still hold if density is not constant. Okay, and I guess one way that you could think about that is imagine you have a tube and there's a bubble in that tube. We have H2O here and air here, and the flow is moving to the right. Well, in this tube, assuming the flow is nice and slow, this flow here, even though you have rho H2O here and rho air here, and they're massively different, the flow is still incompressible. That is the volume of the air. It does not change very much unless the flow is compressible. If the flow is compressible, then the volume of this air bubble can change quite a bit. But we're not going to get into that kind of flow in this class. Okay, but basically you can apply the incompressible flow assumption to a scenario where the density is not constant. Is that if we're to look at the control volume through here, is that as this bubble passes through the system, the volumetric flow rate still holds. So we have the integral of the CS of V dot n hat dA is still equal to 0. Even as the air bubble leaves the control volume, is that basically this still holds. Now, if the flow is compressible and this air bubble is moving at, say, Mach 2, well, that's no longer the case. But so we can apply this concept here that even though the density is constant, is that we still have an incompressible flow. Okay, so we apply a conservation of mass. Okay, and conservation of mass says that the time derivative of mass in the control volume plus the net mass leaving out through the control surface is equal to 0, and this implies that the surface integral, and again this is steady, so we can cross that out, and this implies that the integral over the control surface is equal to 0, because that's the only term that survives. And then I'm going to break this into the 4 pieces. We have area 1 here, area 2 here, area 3 here, and then the sides. Okay, and we're assuming impermeable walls. So we have area 1 here, area 2 here, area 3 here, and the sides here, and we're assuming impermeable walls. So we can cross that out. Which implies that V dot n hat is equal to 0. Is basically what impermeable wall means. Okay, and we're assuming uniform flow. In fact, we aren't given enough to not assume uniform flow. So that means we can basically pull all of this stuff outside of these area integrals here. And I'll just work with one of these terms here, just to show you what happens, is that we can take this rho 2 v2 dot n hat 2 and yank that out of this integral here. That goes outside, and I've done that here. And then we have basically rho 2 v2 dot n hat 2 times the integral of dA2 over the area. And this here is just A2. And so this nasty integral here just turns into rho 2 v2 dot n hat 2 dA2. Okay, so that's it. And if we do the same thing to all of these, other terms here, we have the integral, we have all of these nasty integrals here just turn into a mass flow rate, or a mass flux times an area. All three of them. So we have basically rho 1 of v1 dot n hat 1 a1 plus rho 2 v2 dot n hat 2 a2 plus rho 3 v3 dot n hat 3 a3 is equal to 0. Okay. And so now we need all of these v dot n hats in order to complete this. Okay. And so here, as I did with the previous problem, is I just basically walk around to all the contributing areas that have air, or that have fluid moving through them, and I keep tabs of what v1 are, of what the velocities are, and what the n hats are. Okay, and so this part here is just bookkeeping, and nothing more than that. So for area 1, when it's sort of confusing, I just like to draw a little subsection. So basically area 1 was kind of going in this direction here, where there was water going in. Well, I know that n hat points outside, and so that would be pointing down, and I have fluid going in. Okay, and so that is basically pointing, that's basically pointing in the opposite direction. Okay, so it's an inlet. So v1 and n hat 1 are in the opposite direction because we have flow going inside. We have flow coming from the outside and going inside through that surface. That implies that v dot v.1 n hat 1 is equal to 0. Or we can just look at these basically arrows here and note that this is going to be minus n hat 1 to basically indicate that it's in the negative, it's in the direction opposite. So v hat 1 dot n hat 1 is some unknown v1, n hat 1 minus dotted with n hat 1, and we are just left with a minus v1. And we can do the same thing for area 2, which is the alcohol inlet. Because right here we have some n hat 2 pointing down, we have some v2 going up in the opposite direction as n hat 2, because again that is an inlet, and we can basically form v2 dot n hat 2 again, and we can do the same thing for area 3. That is an outlet, and so here n hat 3 and v3 are pointing in the same direction. So v hat 3 dot n hat 3 is just v3. Okay. Then we take these results here, and substitute them into this expression here, and we are left with rho 1 v1a1 minus rho 2 v2a2 plus rho 3 v3a3 is equal to 0. Well, this here of v1a1 is just equal to the volumetric flow rate at station 1. This v2a2 is just equal to the volumetric flow rate at station 2. And this v3a3 is just equal to the volumetric flow rate at station 3. And this is equal to 0. And what we are after here is rho 3, or the density leaving through the outlet. And so we solve for rho 3. But unfortunately, we know and we don't know v3, but we know rho 1 v1 and rho 2 v dot 2. But we don't know this. So how do we go about finding that? We need v3, and so we just used conservation of mass. Again, the density is on the different surfaces is different, and so we use the general form of conservation of mass. We have not invoked the incompressible flow assumption yet. So let's apply that. Okay, and again, what incompressible flow means is that if I take a cubic meter of material and shove it in through this side over here, that means I'm going to displace a cubic meter of material outside through the outlet. Okay, so I apply the incompressible flow, the incompressible flow condition for a non-deforming control volume. And again, constant density does not make sense, but as I argued before with the trapped air bubble, that we still have an incompressible flow. Okay, so we apply the incompressible flow condition for a non-deforming control volume. And so that means we need to do the surface integral of v dot n hat dA is equal to 0 over the entire control surface. And so I will just include the 3 contributing pieces. Actually, I forgot to add the 4th one, a sides, because I did not, like minus 2 points to Orion for not closing the integral of v dot n hat dA, and that's 0, because it's impermeable walls. Okay. So now, we have already basically formed these above, and I'm not going to go through it again, and if this were a homework problem, I wouldn't make you do so either. And so we have already argued that this here is minus the volumetric flow rate at station 1, and again, this minus sign means that it's an inlet, and so we have fluid moving from the outside, going through the surface, basically moving through area 1 and into the control volume. Okay, and same thing for area 2, and same thing for area 3, and area 3 is an outlet, and basically v3 and n hat 3 are in the same direction, so we have a plus sign here. Okay. So, and note that for incompressible flow, both mass and volumetric flow rates are conserved if it's steady. And for steady, it's just that in most cases for incompressible flow, the density is constant, and if the density is constant, the incompressible flow condition doesn't give you any extra information. Okay, but in this case where density is not constant, but the flow is incompressible, it does give you an extra piece of information that you can use. Okay, so all these nasty integrals just turn into volumetric flow rates going through the surface, or going through the respective surfaces. And so this implies that 0 is equal to minus v dot 1 minus v dot 2 plus v dot 3. And that implies that the volumetric flow rate at station 3, which is what we didn't know, is equal to the volumetric flow rate coming in through the water inlet plus the volumetric flow rate leaving the volumetric flow rate coming in through the alcohol inlet. And so we're going to take this and substitute it into here, and now we can solve for row 3. Okay, then row 3 is given by this equation here. And this here is just the density of H2O. And this here is the density of H2O times our given specific gravity. So I will basically substitute them in. And I'll just call this the specific gravity at station 1. It's water, so it's just 1. But if you want to be general, we can do it that way. And this equals rho H2O times the specific gravity at station 1, which is just 1, times this. So here I'm just basically simplifying it. And we then can now stick in the numbers. And this equals rho 3. And on most problems for your quizzes, I would ask you to stop here because there might not be enough time to stick in the numbers. But now we stick in the numbers. And again, show all unit cancellations and everything like that. But here they're quite easy because there are cubic meters per second here and cubic meters per second here, and they all cancel out, and we're only left with the units of density. Stick in the numbers, and use a density of 1,000 kilograms per cubic meter for water, a specific gravity of 1, a volumetric flow rate of 0.1 cubic meters per second, specific gravity of I thought there was 0.6. A specific gravity of the alcohol, and its volumetric flow rate. And we stuff in the numbers, and we get 850 kilograms per cubic meter. Okay, and so those are the examples I'll give for a stationary control volume. In the next lecture, we will be doing more examples of conservation of mass, but we will extend it to a deforming control volume. And we will show you how you can combine conservation of mass with the Bernoulli equation and manometers.